In this video, we're going to discuss the basic velocity equation, how to use it, what it means, and how to rearrange it. V stands for velocity, and we can find our average velocity by taking the change in an object's position and dividing it by time. Delta x, or triangle x, stands for a change in position. Delta, or the little triangle symbol, you might see next to other variables as well. And it always basically means the same thing, a change in that variable amount. So to find a change in anything, take the final value of that variable and subtract it from the initial value of that variable. Often, you'll see a sub-zero notation to describe the initial value of the variable, or the starting amount for that variable. So for example, if I started at a position of 10 meters, and I ended at a position of 40 meters, well, 40 minus 10, my position change was 30 meters. I traveled a distance of 30 meters. Delta x, or change in position, you might often see written simply as just x. This is because the initial position is oftentimes considered to simply be the zero position, and a number minus 0 is just the original number. You might also see this as d, which could stand for distance or displacement, depending on what's happening in the question. So looking at our equation, we'll notice that our change in position, since it's on the numerator, has what we call a direct relationship with velocity. What this means is, as the change in position gets greater, because the distance an object travels gets greater, as long as time stays constant, the velocity will increase. Let's see an example of this. If I travel 10 meters and it takes me 2 seconds to travel 10 meters, well, then my velocity is 5 meters per second. Notice how the units are transferred here to velocity. Velocity is the rate of distance per time, or meters per second. Meters being the measurement of distance, and seconds being the measurement of time. Now, if we double our change in position, if we double the distance we travel from 10 meters to, let's say, 20 meters, and we still travel that distance in 2 seconds, well, now our velocity is 20 divided by 2, or 10 meters per second. So we notice here that when our position doubled, our velocity doubled. And once again, that's what we call a direct relationship. When one value increases, the other value will increase. If one value decreases, the other value will decrease. And conceptually, this should make sense. If I'm covering a greater distance in the same amount of time, I'm traveling faster, because velocity is the rate of distance covered per time. If I cover a smaller amount of distance in a certain amount of time, then I'm going slower, right? If I only cover 1 meter in 1 second, I'm going a lot slower than if I was going 5 meters in a second. Now let's look at the relationship between time and velocity. Well, we'll notice here that time is on the denominator. We're dividing by time. So time has what we call an inverse relationship with velocity. As time increases, we're dividing by a larger value, therefore our answer decreases, the velocity decreases. If we travel a greater amount of time in the same amount of position change, then we're going slower, right? If I go 10 meters in 5 seconds, well, now I'm only going 2 meters per second. So if it takes us a greater amount of time to travel a certain distance, then we're going slower. So this is what we call an inverse relationship. Now, if time goes down, so if we travel in a smaller amount of time, say only 1 second, then our velocity goes up, right? That's part of the inverse relationship. Time decreases, velocity increases. Now, let's rearrange this equation and use it to find our change in position. Use it to find our distance traveled. Now if we look once again at our equation, if we want to get a variable by itself, if we want to solve for a variable, we have to figure out what's happening to that variable. Well, I noticed that the change in position, my delta x, being divided by time. Well, in order to move time over to the left side of the equal sign, I have to do the opposite of that operation. It would be multiply by time. So if I multiply both sides by time, time divided by time will cancel out. And that'll move time to the left side of the equal sign here. So I get another equation. The position is equal to velocity multiplied by time. Now notice here I just wrote x instead of delta x. For the most part, the same thing, right? Like I said, the initial position oftentimes is simply considered to be 0. So you'll see me writing that as simply x. Just know that that's the amount of position change. That's how far the object traveled. So, for example, if we travel 10 meters per second, and we do that for 2 seconds, well, then we've covered a distance 20 meters. Notice in our units, we're multiplying and dividing by seconds. Seconds cancel out. We're left with meters, which is the unit of our answer. It also matches up with what we're solving for in our equation, right? Position is measured in meters. Conceptually, this should make sense. If I know how fast I was traveling and I know how long I was traveling, I should know how far I was traveling. Let's look now and see what we can do here to solve for time if we know how far we traveled and how fast we were moving. Well, if position, or the change in position, is equal to velocity multiplied by time, if we want to get time by itself, we have to see what's being done to it mathematically. Well, time is being multiplied by velocity. The opposite of multiplying by velocity would be to divide both sides by velocity. If we do that, velocity is being divided by velocity on the right side. Cancel it out. And we get x divided by velocity, position divided by velocity on the left side of this equation. So we get a new equation for time. Time is equal to the change in position divided by the velocity of the object. Once again, this should make sense. If I know how far I traveled, I know how fast I was traveling, I should know how much time it took me to travel. Let's do another example here. If I traveled 20 meters, and I was traveling at a rate of 10 meters per second, well, then I covered that distance in 2 seconds. Now notice if we look at the units, meters are being divided by meters, which will cancel, and we're left with seconds, which is the unit for our answer, and the unit for the variable we're solving for. One important note to make here is that this equation is best used when the object is not accelerating. This equation does not take into account any extra distance traveled due to acceleration. So if you want to know what the velocity is at a certain instant in time, it's best to use one of the kinematics equations, namely v equals initial velocity plus acceleration multiplied by time. But we'll talk about that in another video. If the object is accelerating, what this will tell us is our average velocity. So not the velocity at a certain instant in time, but just the averaged out velocity over our entire trip.